Okay, so next up on our speaker list is Dr. Ashley Gritzman. And Dr. Ashley is a research scientist, also a research scientist at IBM, whose primary research interest is deep learning applied to computer vision. Right. He obtained his undergraduate degrees in electrical and biomedical engineering and completed his PhD at Wits University. And this PhD actually focused on image processing algorithms for automatic lip reading. Can we give him a round of applause as he ascends the stage?
Okay. Great, thank you for the introduction. So like you mentioned, my name's Ashley and I'm a research scientist at IBM Research in Joburg. You heard a talk from my colleague in Devor. We are very lucky and we're probably the only commercial research organization in South Africa that allows us the freedom to do real kind of blue sky academic type research, but in a commercial, in a corporate type structure. So if you are in Joburg ever, please do get in touch. Our whole lab is all focusing on artificial intelligence. We do some more applied things where we work with different partners on different data sets and different problems. And then we also do fundamental things where we try and further the knowledge. But so what I'm talking to you today is about capsule networks. Capsule networks were a very much hyped up and very exciting topic, probably about a year old now. And the reason they were exciting is because they were Jeff Hinton's brainchild. He had been speaking about these things for quite a few years, but only when he released the first of these papers did they actually start to work. And Hinton probably, I hope most of you know who he is. He's now at Google Brain. He's known as the father of deep learning. He did the original, or him and a couple of others discovered the backpropagation algorithm back in 1987. Maybe we'll ask Prof. Marawala to tell us about that. So there are two papers that Hinton and his team published. I'm going to be trying to give you a bit more of an intuitive understanding of the first paper, which is dynamic routing between capsules. If you are familiar already with things like CNNs, convolutional neural networks, you'll be in a very good position to take away almost all of the messages in this talk. If you haven't heard of those, then you'll at least be able to extract the ideas behind capsule networks. So we'll cover a few things. Firstly, why capsule networks? So what's wrong with CNNs? We'll discuss the idea behind them, how they work, and then I'll briefly touch on the results from Hinton and some work that we're doing at our lab. Okay, so the first question, what's wrong with CNNs? So CNNs are really good at detecting features, and what we mean by detecting features is you see the face up over there, and the CNN can quite easily be trained to say this is an eye, this is a nose, this is a mouth. That's what we mean by detecting features. But CNNs are not particularly good at understanding the relationships between these features. So what I mean by this is if we give it this image, a CNN will most likely say, okay, well, I see two eyes, I see a nose, and I see a mouth, and so therefore I must have a face. In this image, okay, so each of those numbers is a probability of detection, and the CNN says, okay, I've detected each of these features with a high degree of certainty, and therefore I have 95% chance of seeing a face. Well, what we humans can easily say is, no, okay, that's not a face because the eyes are not the same size and the mouth is at a different rotation to what you would expect for the eyes. So that's what we mean by CNNs are good at detecting features but don't place importance on the relative positions. And Hinton says, blame it on max pooling. So he said the pooling operation used in convolutional neural networks is a big mistake, and the fact that it works so well is a disaster. So he said it and not me. But so what he means by it's been proven empirically that max pooling is useful and makes a big difference, although in some later some more recent architectures, it's becoming less popular again. And the reason he says it's a disaster is because it doesn't make sense to throw away this information, but the fact that throwing away this information is helpful makes it really hard to stop doing it. It's like you've developed a bad habit, but that bad habit actually is productive, so you can't get rid of it. And so intuitively what's happening, what he means here is, okay, we have a 4x4 over here, and let's say we have a feature for an eye and parts of the mouth over there. The pooling operation would take that and make it, pull that down, let's say take the feature it identified and make it into that nice face that you see in the middle. Okay, that makes sense. What happens in the case on your right over there, and you have these features, but now the spatial relationship is all messed up. And what you can see is, okay, well, still applying that same pooling operation gets you back to that nice pretty face in the middle, which is actually not what you had. So this is a kind of an intuitive understanding of what's going wrong here. The second problem with CNNs is that they use layers to capture different variants, and as a result, CNNs can't extrapolate understanding to new viewpoints. What we mean is you have our faces, and they're getting rotated, let's say, by 20 degrees either way. How does a CNN learn this? Well, it has a bunch of different neurons that learn these different variants. So these things are obviously very big because each different group of neurons learns these different variants, but it now struggles to say, okay, what will a face look like if it was at 30 degrees or at 40 degrees when it's only been trained on, say, -20 to +20. So the idea behind capsules is drawn from computer graphics. And what happens here in computer graphics, you have a representation, a geometrical representation, that is independent of the pose. So what we mean is you see that kind of 3D mesh structure. That's what the teapot looks like, independent of which angle you're looking at it from. And then when you actually look at the teapot, you have your particular viewpoint, and that's when it gets rendered into the 2D image that you see. But the representation inside the computer is a 3D representation that doesn't depend on that pose. And so this is where it came with the idea of inverse graphics. So he says, okay, our brain does the opposite of what the computer does. So it takes our 2D images and tries to, in our brains, construct this three-dimensional object. And if it can't do that, then obviously you're not constrained to having only seen it from a certain viewpoints. Okay, a question. So do you recognize this? Okay, so most of you probably recognize this. If I give you another one, you probably, almost all of you recognize it. It's the Statue of Liberty. And so how have you done that? Well, I would argue almost none of you have seen it from the viewpoint in the first picture. And so what you realize here is your mind can work out what you're looking at, having never seen this from these specific angles. You've seen it from other angles, but the representation that you have in your mind is not dependent on your viewpoint. And this is the idea that Hinton's going for in these capsule networks. So moving from CNNs to capsules. Okay, in the first column you see problem 1, the spatial relationships. So what capsules do is instead of just detecting things well, so now we learn what we call instantiation parameters, which are just different properties of this feature. So for example, each of those features now have 3 numbers. The first is the probability of detection. That's kind of what we saw before. So how confident am I that I've seen an eye? The second in this example is a number representing rotation. The third is a number representing scale or a number representing size. So no longer are we only interested in just detecting something. We actually want to know things about that feature we've detected. And if we can do this, let's look at the mouth, for example. The mouth is at a rotation here, and when you compare the rotation of the mouth to the rotation of the nose, you realize, okay, no, something is going wrong here. Even though I've detected a mouth and I've detected a nose, their rotations don't line up. Or in the case of the eyes, the scale, the size of the eyes don't line up. And so if you can achieve this, then you can say in our problematic case, no, we actually haven't detected a face. And if you can achieve this type of model, then the extrapolation problem is solved quite easily, in that it's now you have one group of neurons that learns all the different variants, so learns all the different rotation angles that you're interested in. And if you can, then it's much easier to say, okay, well, I've learned from 0 to 20 degrees, but now what does it look like at 30? The network would be much better at understanding things from viewpoints it hasn't seen before. Okay, so how do capsules work? This explanation I'm borrowing from Aurélien Géron. He's the author of a book, Deep Learning with TensorFlow. And the reason I'm borrowing is this is a thread on Reddit which discusses this video. And Hinton wrote himself, this is amazingly good video. I wish I could explain capsules that well. To which one of Hinton's collaborators, Nick, wrote, well, we all wish you could explain capsule networks that well. So a really great video that I'm borrowing some slides from. You can go find it on YouTube if you want the detailed explanation. Okay, so we start from where we said. We're going from our representation, our computer graphics representation, to our image. In this case, we're just talking about a rectangle and a triangle that each have a position in space, so an x and y coordinate and an angle. And remember, what we're trying to do now is trying to do inverse graphics. So given the image of the rectangle and the triangle, can we work out where the positions were and what the angles were? And the way capsules do this is they do something called inverse rendering. So it starts off with applying a few layers of convolution, standard convolutional operations, to get out a feature map. So, okay, what you're seeing there with the arrows, the length of an arrow tells you the probability of a feature being at that position, and the angle of the arrow in this example tells you the rotation. So the blue arrow tells you, okay, at that spot in space, you have a high probability of having found a triangle, and the triangle is rotated by that amount. The black arrow tells you a similar story for the rectangle. It says at that point in space, you've got a rectangle with that probability. Now, all the places where there's not a rectangle, those vectors that it has should be very small. And in this case, okay, all we're representing is the rotation, but you could represent much richer feature vectors over here. You could have rotation and scale, and in fact, actually, these features are learnt through backpropagation. So you can't really say, I want this to actually represent scale and rotation. These are learned, and you kind of hope that the things that are learned actually correspond to some properties in the real world. It would be even nicer if these properties are separable. Okay. So how do you do this? You apply a few convolutional layers, then you reshape and you squash. Okay, so to understand that, if you understand CNNs, you can apply a few different kernels. And let's say, for example, you can apply 20 different kernels, and you come out with an activation space of 20 features. And I can take those 20 that now I have, and I can divide them into 2 vectors, each containing 10 parameters. Or I can split them in a different way. I can divide them into 5 vectors, each containing 4. So the first layer is just standard convolution. And then what we mean by reshape is we take these layers that we've got and we arrange them nicely into these vectors that we want to work with. So in the paper, you'll see this is the main diagram. And so it starts with a nice MNIST digit, and it applies 256 convolutions, and so that gets you to the ReLU conv 1. And then those are another 256 applied. And then the splitting is just taking the 256 and now dividing them into capsules, each having 8 instantiation parameters, and it's got 32 of these capsules. So if you see that figure, you have a bit of an understanding what's going on. An important property in capsules is the property of equivariance. And what this means is it's different. You might have heard the concept of invariance. So invariance is, okay, if something moves around, but it's still the same object, then I should still detect it with the same the same probability. So nothing should change. That's what invariance means. Equivariance is slightly different. It's that if it moves around, I should still detect it with the same probability, but I should be able to detect the change. So in this, it's just the boat that's moving a little bit, and you can see what we want is for our vectors to rotate in a similar manner. That's the property of invariance. Okay, so now let's say we can identify this lower level things of the triangle and the rectangle. How do we build up higher level objects? And so we have a hierarchy of parts. What we mean by this is we say, okay, a boat is made up of a triangle and a rectangle together that form a boat. With that same triangle and rectangle, you could also form a house. And the difference is the spatial relationships between these things. They're made up of the same components. So when we are in a capsule network, what happens is the first layer is the primary capsules, when we try and identify the most basic features that comprise those things. So the smallest building blocks. And then what we're going to try and do is piece those building blocks together in a way that makes sense to build bigger objects. So our first layer would take our image, we don't yet know what it is, and decompose it into, okay, triangles and rectangles. Then the next place is where the magic happens. That's the dynamic routing algorithm, and that's, okay, how do we combine these lower level pieces and how do we put them together into an object? And the way this works is that each lower level capsule has to predict what the output of the next layer would look like. Okay, so that's a bit of a mouthful, but what we mean is this. The rectangle, that has to say, if the rectangle says, okay, I'm a rectangle, and if I was part of a house, what would the house look like? Okay, it would look like a house slightly rotated. And if I'm this rectangle and I was part of a boat, what would that boat look like? And it says, okay, you'd have a boat slightly rotated. Okay, good for the rectangle. Then the way it does this is it has a transformation matrix that says, okay, how would I transform myself to being part of a boat? Okay, now the triangle will do the same thing. The triangle says, okay, I'm a triangle. If I was part of a house, what would that house look like? And if I was part of a boat, what would that boat look like? So now we've got the predictions for the next level from the lower level. The rectangle said, what would I look like? And the triangle says, what would it look like? And so straight away you can see, okay, the predictions made for the boat from the rectangle and the triangle both agree. But the predictions made for the house by the rectangle and triangle don't agree. And this is where we're looking for, they call it coincidence in higher dimensional space. But we're looking for the lower level capsules to all agree on what the higher level output looks like. Okay, so like we said, we have, for the boat, we have strong agreement between the lower level capsules of the triangle and the rectangle. But for the house, we don't have that agreement. Okay, and so what we're doing here is we're looking for clusters of agreement. So on the x-axis, what that's representing is a rotation, and on the y-axis, that's representing the size of the boat. And all these blue points would be votes from a lower level capsule. And so you can automatically see, okay, where's the cluster? Where do most lower level capsules agree? And the algorithm is similar to a k-means. You might, we won't go into detail here, but okay, you'll see that the algorithm finds the mean of the cluster and says, okay, so I figured I've got a fairly big boat with this amount of rotation. Okay, and if you have a look at the paper, you'll see it's the routing algorithm over here that does this. How does it actually achieve this? Okay, so what it does is when you have a standard CNN, once you've trained it, the weights are fixed. And what we mean by that is if you feed in some input, it follows the weights and goes through the layer in some fixed sort of way. Hinton's idea is called dynamic routing, and that is the routing, so where things go in the high level, is actually determined only at the runtime. And so how does it do this? Okay, so the lower level capsules will initially have their output of, let's say, a total of 1, and they get to decide how to distribute that. So which higher level capsules get to have their output. And so initially they don't know anything, so they just equally give all the higher level capsules the same amount of their output. And that's represented by each of them getting, say, a 0.5. They all get their 0.5, and this is then used to weight the outputs. And so you sum up the outputs for the house and the outputs for the boat. And then the fact that it's gone more to the boat, then we feed that back to update these routing weights. So, okay, we see, okay, the boat that we predicted has a similar form to the boat in the high level capsule, and we say, okay, there's agreement here, so we must route more of our output there. And how we do this, okay, so we go through and we update these routing weights, and if there's disagreement, then we must reduce these routing weights. We won't go into the detail there now. And so in the next iteration, you see both the rectangle and the triangle now feed more of their output to the boat and less of their output to the house. And eventually, after a few iterations, we'd want it to arrive at the stage where the boat gets all of the output because we've decided, no, this rectangle and this triangle form a boat and not a house. Okay. In the realm of the face that we were talking about, the parallel is this. So the lower level capsules might be detecting the eyes, the mouth, and the nose. And this transformation matrix that we've spoken about briefly that says, okay, how does the eye fit into the face is that W that you see. And then those are all summed together and squashed. And what you get out is, if you see those colored ovals, those are kind of the faces predicted from the different features. So the eye gets to predict what the face should look like, the mouth gets to predict what the face should look like, and the nose gets to predict what the face should look like. And if they all agree on what the face should look like, then the high level capsule says, okay, we've got a face, and this is the pose of the face. And once you've built this model, the actual last part, which is the classification, is quite simple because we've said the length of the vector represents the probability of something being detected. So all we do at the end is say, okay, how long is the vector for the house, the vector for the boat? If the boat is the longest, then we say, okay, we seem to have identified a boat. They also add on one cool feature, which is they do reconstruction. So now remember that we've got a vector output instead of just a scalar. You know, a normal CNN gives you just a scalar on the probability of, each thing that you've detected from your softmax. And now we've said, okay, can I use this vector to actually reconstruct my object that I was detecting? And so you train the network with this whole reconstruction part. And the reason they do this is it helps with regularization. So it gives you a better generalization. Another benefit of this is now you have a network that can reconstruct these pictures from vectors. So if you tweak or move that vector around, as I'll show you in a little bit, you can build different looking objects. And so this is what their decoder looks like. It's just a couple of fully connected layers. So they'll take one digit and reconstruct it back to a 28 by 28. Okay, so the results from the paper. Some of the pros, that these capsule networks achieved a high accuracy on MNIST and provided a pretty good start on CFAR10. They seem to require much less training data. They have this property called Equivariance, which is great. And they offer a bit of robustness to certain transformations. And what that means is if things rotate, you can still kind of figure out what the object was. Where the shortfalls were some of the cons from the paper, they weren't state of the art yet on CFAR10. The big question on how does this thing perform on a big data set like ImageNet hasn't yet been well answered. And probably the biggest problem with these is that they're really, really slow to train. And this is where the work is going on at the moment. How do you approximate this algorithm or change it in some way that you can train these things much faster? One pro that we mentioned is, so you've got this vector output, and so this is what they show in the paper. What happens if you take one of those dimensions and tweak them? How does the reconstruction look? And so just looking at the first row, scale and thickness, they took one dimension pertaining to a number 6 and just tweaked it a little bit and reconstructed the different images. And they said, oh, okay, the network at that point had learned scale and thickness. And in the second row, the localized part is the arc of that 6 at the top. And so this showed that these capsule networks were learning things that actually had meaning. What we were doing at IBM is we said, okay, these could have the very cool property of being able to handle rotation much better. So we were looking at a data set that was to do with melanomas. So melanomas are moles or skin lesions. And what we said is, okay, if these handle rotation, then they should do pretty well on the melanoma data set, because these images were captured with a handheld camera. So you can imagine if a doctor's holding a handheld camera, they could be holding it at any angle. It's arbitrary. There's no kind of hold it at that angle. So that's the question that we were looking at our lab. To mention, there has been some work in the past couple of months. This is a couple of months now, a couple of months old, by Lee and his collaborators, and he claims to have managed to modify the capsule architecture in a way that he's got competitive performance on CFAR 10 and CFAR 100, and some very promising results on a subset of ImageNet. I won't go into too many details, but basically what they say is, okay, instead of doing this routing algorithm where everything goes to everything, so what I said is all kind of triangles and rectangles go to everything in the higher layer, he's simplified it in that there can only be 2 branches, he said. So there's a primary branch and a secondary branch. That was the first simplifying assumption they made. And the second one, they said, okay, they did away with this dynamic routing, this iterative process. And the reason, so they threw those 2 concepts away, but in exchange, they've got this network that's much more efficient. And if it's much more efficient, then you can train it a much, much deeper network. So that's what they did, train these much deeper networks, although slightly simpler approaches, and that's how they've got their competitive accuracies. The capsule networks are about a year old now, so there was a question on Reddit that said, what's the status of them? And Nick Frost, who's one of the authors on the papers, said, okay, they're still working on it. Mainly, he said they're grappling with how to improve the efficiency. And he also made a comment and said the recent paper they published showed that they were a bit stronger to adversarial attacks. My take on it is that there seems to have been a lot of initial excitement, which obviously slows down as you get into the real work with anything, but they're still being worked on. And the last slide that I like to share is this humorous picture from Andrei Karpathy. In this picture, if you look at it, you hopefully think that maybe that's a little bit funny. And so the question I ask is, what would it take for a computer to be able to understand that this image is funny? If you had to think through all of the things that you actually, all of the pieces of information that you combine to laugh at this picture, if you list them, in this picture there's 3 mirrors. If you look carefully, you'll see them. Your algorithm has to understand that these mirrors are artifacts and not people. You'll have to identify that, okay, that's Barack Obama from just a few pixels in his face. You'll have to identify that that man is standing on a scale from it really blending quite closely into the white background. So how did you know it was a scale? Well, probably because you saw what pose the person standing on it was doing. So you probably figured out it's a scale, not from the pixels comprising the scale, but from his pose. Then some higher level things is, okay, you looked at the people standing around and they were all smiling. So what you said is, okay, you also have an understanding of the law of physics. You understood that by Barack Obama applying some pressure in 3 dimensions onto that scale, that would have given the scale a different reading. And the person reading the scale would then be surprised by a higher number than he expected. And you also know that people have consciences about their weight. And so the people are laughing at what they think that the person standing on the scale is looking at, is thinking about. So what are we laughing at? We're laughing at the things that the people laughing at think about the person standing on the scale. So the long and the short of it is that computer vision still has a long way to go, and while we have made some massive progress in the past few years, the field is still wide open for research.
Can I
Hi,
have some questions?
thanks for the really great talk. Just wondering, how robust are these networks to adversarial examples?
Yeah, so that's a great question. That's probably one of the strengths that they're focusing on at the moment. In that Reddit post, Nick Frost has a link to a paper they published recently. Over there you'll see the link. So if you search for it, you'll find it quite easily. They compare a standard CNN versus these capsule networks in the case of an adversarial attack, and they've showed that the capsules they're more robust than a standard CNN to certain types of attacks. So if you're interested in that question, they've done quite a bit of work, and it's a great new topic to look at.
I don't know the details of the architectures of the capsule network. So what I still find strange, so basically, if you have different data set and you test it, obviously you train your network, it learns different types of features, right? Or is it always skewness of a feature? And it's always, so do they appear over and over again? And is there anything that you can give me an intuition for where you give the network a hint, please learn these features? Or is this just, it seems that this is what the optimization algorithm just picks out from the data for some strange reason that no one knows? Or is there anything in the architecture that says, do this?
Yeah, so in these examples, we don't force, they don't force the algorithm to learn anything, and they're very relieved to see at the end when they start tweaking things that it has learned things that seem to make sense. We have thought a little bit about ourselves doing some disentangling. So what you see here is it learns interpretable features, but they're not separate. They're not clearly separated. Like what we would want is one feature that learns rotation, another one that learns position, another one that learns thickness of the line, like things that you can pull apart nicely. So they didn't impose any external constraints, but we had thought a bit that you can actually manually kind of tell it to learn, tell it what you want the parameters to be. To your data sets, yeah, so this is because it's being trained without any external constraints or external objectives to force that, it gets to learn what it wants, but it does land up usually learning things that make sense, and that is kind of what you'd expect. You're relieved to see that it is learning those things, because at the end of the day, it is a visual system, and so the features have to be visually present in the object. I can't tell you of anything I've seen that does that disentangling process, and I think it's certainly a cool thing to look at. Perhaps there could be some inspiration drawn from the variational autoencoders, where they learned the beta variational autoencoders to kind of force these things to disentangle a bit. Yeah, I hope that partially satisfies your question. Any other questions?
Thanks for the talk. Just a quick question. Has any work, to your knowledge, been done in the way of incorporating SIF descriptors for like localized features as a starting point for capsule networks? Because if you're wanting to capture, let's say, strong features in an image, perhaps using SIF features or some equivalent would be perhaps a good starting point if you're trying to specifically look out for hard edges or noticeable features in a data set. So I was wondering if you had seen anything that incorporated it into that?
Yeah, so I think this takes you back to the realm of kind of designing features versus learning features. To answer your question directly, I haven't seen anything like that, and will it benefit these kind of algorithms? Perhaps, maybe or maybe not. What they're trying to show here is that you can learn the whole thing, including the very bottom layers of features, on its own. They're trying to show, okay, if you set up your architecture in this way with these transformation matrices and, you know, these are the weights that you can learn, then you can learn things. It seems that the trend is away from features like that, but it may benefit. Yeah, let me know how it goes.